Was that SP College or Pune?
Pune. It is in
Yeah,
Pune,
right.
Pune College. So a couple of weeks were there.
Yeah, right. I think you were there for 2 weeks.
2 weeks in
Yeah,
1996.
right.
That's a major association.
Yeah.
All right.
Though after that he somehow couldn't make it.
Not that we didn't make efforts, we did.
Yeah, MTTS did make effort.
Right.
Somehow is not
You-
a fault of MTTS for sure.
No, it's nobody's fault anyway. I'm just saying. Yeah,
Yeah, it's get involved in many other things,
that's
and
right.
that's a reason.
And also when you are young, the career also matters. Okay,
Yeah, it's
that
career and
consideration is more important.
so it,
That's what I tell my youngsters also here. Okay, take care of your career. Don't spend too much time on MPTS also.
So
Yeah.
now I'm more relaxed because it's a fag end of the career.
Well, that will be long innings.
Yeah, but so that's why spending on these
Yeah.
books and things like that. So that's why I thought I will at least this ODE, PDE will have online at least some lectures. So we have full
That's why,
course.
it will prepare you for that.
Yeah.
All right. So get involved with MTTS. We will give you a lot of opportunity so that, after retirement also, you know how to be useful to the society.
Yeah, that's true. That's true. So,
Okay, we can start now.
yeah, sure.
So,
That is SP College or?
okay. So, good evening, everyone. Welcome back to the second day of Career Days 2024. I am Chaitanya Sheth, a PhD student at MS University, Vadodara, and I will be the host for this talk. As I mentioned in the afternoon talk, today is a quite special day for the Career Club as the club turns 4 and our guiding light, Professor Kumaresan, turns 74. On this special occasion, we have another special speaker. The invited guest for the evening is Professor A.K. Nandakumaran. He is the chairman of the Department of Mathematics, Indian Institute of Science. Recipient of many awards, Professor Nandakumaran has got his PhD from Tata Institute of Fundamental Research, Mumbai. His primary areas of interest include analysis, ODEs, PDEs, control theory, and differential games. He has also authored numerous widely used books as well as given some NPTEL course on ODE and PDEs. Professor Nandakumaran, as he mentioned, was associated with MDTS during the very initial days. Many of us often believe that not very rigorous mathematics is required for studying differential equations. That's why, to break the myth, Professor Nandakumaran is here with the talk titled "Importance of Rigorous Math in Differential Equations." During the talk, if you have any questions, please let us know through the comments and we will request the speaker to answer it either during the talk or at the end. And YouTube viewers may post their questions in the live chat. Sir, I thank you for accepting our invitation. The floor is all yours.
Thank you very much, Chaitanya, Tamoga, and all that. It's my pleasure to come and give a talk. Since I do not have much idea about the audience and their background, so let's see after the comments. Probably next time I can prepare much better. So, as I said, we see differential equations not only in one institute throughout. It's actually introduced as a problem solving. So you look like the problems are artificially created, but never realize that ODE or PD is basically a course on analysis. So if you want to really understand any differential equations, you have to have a wide variety of fundamental courses like basic analysis, measure theory, functional analysis, differential geometry, complex analysis, and much more. So basically, that's also a reason probably if you want to have a good understanding of your differential equation, you need to have a thorough knowledge of various topics which you only master during your masters. So probably it's a bit difficult to show the importance of analysis during your masters and PhD students, masters and graduation time. So you get to know about it much later. So there is a kind of a difficulty if you want to do good research or good understanding of differential equations. You need to have a good knowledge of the topics, most of the topics which you are studying during your MSc. So, and also I understand most of the participants may be from the final BSc or second BSc or MSc and maybe something. What I'm going to do is that after discussing with Chaitanya, so I'll be taking a couple of examples which you already know it, probably coming from the applications. And I will try to show that what you do it during your MSc course, how you just solve it and leave it at that. And just to indicate that that's not enough. At the end of it, there are several examples. So I will want to see 2 or 3 examples today. So let me share my talk and then is that visible?
Yes, it is visible.
Okay. I will try to make it a full screen. Yeah. So I given, I think this is a curry leaf, right? And what is given there. So, so let's start with it. So I'll give a some introduction, very quick introduction. And I want to have a couple of models like a population model, atomic waste disposal problem, spring-mass-dashpot system, and I'm not sure I'll be able to reach everything there. And sometimes you solve the problem in some modeling and you may have a complete answer, but that will answer may not satisfy the society because the problems are coming from applications. It may not satisfy the applicants about it. Sometimes so you may have to change the model. When they change the model, you may not have the complete answer. So it's always an issue. How do you model these equations and how do you solve it? What are the requirements and how do you answer the applications? How do you really tell the thing? So maybe the problem is coming from the government. Maybe I will show you that one. So I will start with something. So let me give you a popular. So differential equations at the heart of analysis. That's what I think. But just analysis is not enough. You have to have a good understanding of your linear algebra, functional analysis, complex analysis, differential geometry, all that is required. But we treat all of them as basically analysis. End of it. Okay, so early development, how do you problem started? You have classical problems by the scientist. Scientists pose classical problems to that. That's where the development of differential and integral calculus started. A lot of things to say about it. As I said, I will not get into all that. And then realization that obtaining a solution in closed form or in implicit form is nearly impossible in most of the practical problems. This is the point you have to understand. When you study ODE or PDE, during your bachelor's time, you try to get a solution in either in a closed form, in an implicit form. And what I'm saying that these are all typically pathological examples. Most of the practical problems, you will not be able to solve explicit solutions. So then what do you do? Because it's a practical problem, you have to give that one. That's where probably the numerical analysis, computation, scientific computation, all that coming. But before doing scientific computation, you have to provide them some answers. That's where your mathematics is required. Okay, so various developments happened after the differential and integral calculus, like Fourier series. If you look at Fourier series and integration, these are all introduced in the process of solving differential equation, not necessarily ODE differential equation. Today, I am only restricting to ordinary differential equation. I will not get into partial differential equations because that needs much more deeper analysis. Here, you need only analysis which you know more or less. And integral and differential equations, complex, and a lot of things like linear algebra, functional analysis. These are all happened over the last 200 to 300 years after the differential and integral calculus. You can see that. So then there are concepts like initial boundary value problems. In your thing, people say that this is an initial value problem, this is a boundary value problem. But why? You should start asking questions. Why problem, ODE problem, initial value problem is valid? Why a boundary value problem is valid? So there are questions to be asked. Most of the time, these are all not answers during your masters. Then there are solutions. What do you mean by a solution? I said most of the time you don't get a solution in the closed form or an implicit form. Then what do you mean by a solution? Is solution, so our understanding during BSc and MSc is that solution means you have an expression. U is the first solution, Ux equal to. It's not that. Solution, there are various kinds of solution concepts developed, especially in the last 100 years. And then that's where your requirement of mathematical analysis to understand that solution means what. So there are various things to it. Then there are notions like existence, uniqueness, continuous, dependence. Why do you need such things? There is a solution, is something like that. You may not be able to find the solution, but you can say that there is a solution. This is important even to, if you want to solve, give numerical computation, and there are how many solutions, and there is a continuous dependence, because in practical problems you always make corrections, errors. But if you make some errors in the given data, how your solution will change it? A small perturbations in your data will change large perturbations in your solution. This is precisely the notion of continuity. To do that continuity, where do you check continuity? And you need the appropriate spaces to do that. What I'm telling is that what I'm not going to do all these things. So these are all where you need to require a strong mathematical background. Then you have a qualitative analysis. You may not even have a need to know the solution of a differential equation. Quite often you need to know what happens to that. You need some property of the solution. What happens to the solution when after some time? So suppose it's a time independent solution. Initially, you may not be bothered about it. So for example, you are launching a satellite. All the time you may not know what's happening to the trajectory. Probably you want to know the trajectory will reach a particular place. And then there are concepts like phase plane analysis, and geometry comes into picture in the phase plane. You sometimes need to understand it geometrically. Okay, and then of course at the end of it, methods to solve, numerical and scientific computation, an active area in the current research. And what you are doing in BSc and MSc time is only methods to solve ODEs, nothing else. Not before that you don't study anything. And I told you the main reason to understand all these points 1, 2, 3, 4, etc. you require a strong mathematical background. And methods to solve probably you don't need initially. Of course, when you want to do numerical and scientific computations in a scientific way, you need to know the previous points. This is where you want to do it. And then some issues always faced by the students and teachers in our thing. Quite often you write dx dy because these are all not introduced. And quite often you write fx dx equal to fi dy. What does that mean? How do you interpret that one? What is the meaning? You make a change quite often, right? Quite often you write in, even in integration, y equal to t square. Then you write dy equal to 2t dt. And this quite often, this is my own experience. When we are in BSc and MSc, we don't understand. When you write the y square, y equal to t square, you write dy equal to 2t dt. What does that mean when without introducing dx, dy, etc.? Okay, and and another thing, why a constant is appearing while integrating. So we will have a lot of small pricking doubts in our mind, and quite often such things are not clear. And this is where you have to understand things properly. So when you study a first order equation, ODE, you add one constant. Why? And then the reason is that it's a first order ODE and hence one's constant. That's not the exact way of telling. Okay, then when you solve two constants for a second order linear equation, why two constants? So to understand for that, you need more of mathematics, the modern mathematics to quite often to understand. It may have a physical interpretation, but you need to know that one. Okay, and then one thing which ignore and never introduced to, we studied this separately in analysis, but this is not connected to it. You write f of y equal to, and this is the change of variable formula. So whenever you are studying certain integration theory, it's important to understand whether there is a change of variable formula. You would have seen this formula in analysis, but quite often when you study ordinary differential equation or partial equation, quite often this is not connected to it. And understanding such a change of variable formula is also important to understand the concepts dx, dy. In the initial, of course, there are more differential geometry way of understanding. I'm not going into that way. I want to understand in the beginning stage. How do you do that one? So these are the kind of doubts which thing. Of course, I will not be able to tell any of these things right now. That you may require hours of lectures and other occasions. And other questions you can keep on asking about it. Okay, so some questions at some point of time, at the end of it, if possible, we'll answer to you. Now let's go to three models, which are one is the population model I want to write. What is the population model? So you don't try to read everything. So this is written some few things in the slides. So somebody wants to read these slides later, you can read that one. So what is this population model? The YT is the population given of a species. So it's important how the population grows. So the rate of change of population in a very simple form, it need not be always true. That's what I say, various models are there. In a normal case of population, how the population increases because of the death rate and the birth rate. If you have a birth rate minus death rate, that would be the thing. So if you look at it, the population and exactly the rate of change of the population and no other influence. That's what you have to understand. Of course, the population of a city will change not just because of the birth and rate. The population, immigration will be there, immigration will be there, there will be natural disasters, all that will think, and other species will also influence your change of population. I'm not taking into account. In a very, very simple situation, the change of population, the population changes with the rate of change of population will be proportional to the YT itself. Because the population is, suppose you have a population of 100 and there is a population of 200. Naturally, the change in population is the double in the second case. So that's why it's called, so if you have 100, the population changes to 110 in the first year and birth rate and everything is in the same way. The population with the 200 population, it will change it to 220. That's what I said. So, and the rate of change. So that leads to the one of the most easiest and simplest model. That's what I want to take it, dy by dt equal to RYT. So where R denotes the between the birth rate and the death rate. So now we want to know that how the population is grows. That's very important. So what do you do it in as a PD? You want to solve this equation. You whatever method you want it. You method which I want to prepare, you get a method here. Yt will be y naught into, if Yt naught is equal to y naught is the initial population, your pause. So you ask for this is where you most of the time the students stop. You have dy by dt, RYT, you obtain the solution, done, period. That's what you do most of the time. That is where actually the analysis begins. What do you want? You want to know the change of population, right? How the population grows. You as T changes, whether the population will explode. It's important because if it's a human population, you want to develop your, if it's a city population, you want to develop your infrastructure for that population. This data is important for the society, or if it is a bacterial population, you have to administer your medicine according to the change of population, how rapidly this population goes and how fast, how does it go. So one of the important thing is that what happens to your population YT as T tends to some T bar or T tends to some T infinity, how the population of the city grows. So you know that immediately if R is positive means you have a birth more than the death. Okay, so naturally from this, the first simple analysis is that the exponential goes to infinity, and you will immediately see that. So that also motivates an initial value problem is that the only data which you require to analyze this simple model is the rate of change of population, that proportionality constant R, and then the initial population, right? So that leads to a motivation of the initial value problem. All right. So what is the thing? So as t tends to infinity, yt tends to infinity. So if you restrict to this simple model, your population goes to infinity, and no city can sustain that population. If it's a bacterial population, you will die. Naturally, if the bacteria goes to infinity on your body. So this is a model, reasonable model when the population is small. You see, your validity of, that's what you have to understand from this analysis. The validity of your population model is true when your population is small. It doesn't matter. But the population becomes larger and larger. That means you have more births. Naturally, your population will go to infinity. That will go to infinity exponentially, very fast, as is happening in our city now, basically. So indeed, the about linear model is found to be accurate when the population is small. It cannot be a good model as no population in practice can go to infinity. So this simple analysis immediately tells you this is where your analysis required in all the models. Okay, there will be competition with each other. For the limited space available for, this is where a competition you have to take into account. So when the population goes, it will increase the demand. You will have only one house for 2 people or 4 people. What do you do? Or you will have only one medicine and 2 people are there, patients, but you have only one medicine. If you don't administer the medicine, one of the patient will die naturally. So what do you do? If you have only one food for 10 people, the people will start fighting each other. So you want to understand a statistical averaging of the fight between them. So if you have only 2 people, there will be only one fight. But if you have 3 people, there are 3 fights. If there are 4 people, you will see 6 fights. So you see the number of people, if n is the number of persons in the population, you will have 1 plus 2 plus up to n minus 1 5 interactions between them, and that will be order, that's n into n minus 1 by 2, and which is of order n square. So if you, the interactions between the people is of order so n square or y square. So yt is the population, the interactions, the average is that one with some ratio. So you see, that's what I said. So you are trying to analyze the model. Statistical average of the number of encounters of 2 people per unit time is proportional to y square. And then people will start fighting each other. For one medicine, people will fight each other. One of them will die, other person will die, survive. Then only he can get the medicine. He can get the food. So that leads to a model. A better model would be, so you see, the first part is a linear part model, which changes your population according to the A, and then you have a model y square. Not that everyone fights each other, so there will be a fraction. That depends on what type of population you are analyzing. For a bacterial population, it will be different. Human population in a city, it will be different. And this even for a particular city, over a period of long period, 100 years, you may have to change this parameter. But to begin with, you will have A and B are constant given, which are positive for the time being. Okay, if A is negative, nothing to do. The population will goes to 0. You won't have anything. The problem comes when there is a mode birth. So you want to, so you see, earlier model was simpler, but easy to solve it. And that's not satisfactory. So analyzing that, you change it to the model, again an initial value problem. This taken to represent computation, which reduces the growth rate. You see, there will be computation for the space, computation for the food, computation for water, competition between for everything. That's what is happening in most of our cities. There'll be competition because we don't have enough infrastructure, we don't have enough food, we don't have enough water when the population grows suddenly. So the city planners, the government has to plan for it. So we have to have an idea how the population will be after 10 years, 15 years, 25 years. Accordingly, we have to develop the infrastructure. Unfortunately, that's not happening. That's why we have problem, because we don't plan it for the 20 years, 25 years, 50 years later. So now I want to analyze this problem. Can I solve? First of all, first thing is that as soon as you get an equation, you try to solve it. Can we solve that? I told you most of the time, solving nonlinear problems is not that easy. Fortunately, this problem is easy. This problem was introduced by a Dutch mathematical biologist in 1830, almost nearly 200 years back. And this is called logistic law of population growth. So let's try to understand. First step is try to understand the solution, whether we can solve. Even without solving, you have to analyze it. That's what I want. That's where your analysis coming into picture. Sometimes you will not be able to solve, but still you will be, the idea is to, where does the YT goes? Can I reduce something? Okay. Interestingly, this equation is solvable using partial fraction because it's a nice thing. So I will not do it. This is, I'm sure you would have seen this problem. You can, because it's y into a minus by, you can make partial fractions and you can integrate. And then you can get the solution. If you can think, one of the mistakes quite often people make is about this model. There is a modulus here also, okay? Y by y naught also there is a modulus. Somehow I didn't correct it. You have to correct that also. And there is a modulus. What do you do? So this is what you do it in your BSc or MSc. You just produce this thing. I solved it. How do I? What do I do with this? Well, how do I give? I'm interested in understanding the behavior of YT. As I said, there is a modulus. It's a log mod y by y naught into mod a minus by naught by ay. So how do I get a solution now? Why? Can I get an explicit solution? Can I do something? Because I can modulus, I am not able to remove immediately. I can take it here, but I do not know how do I remove the modulus. If I remove the modulus, I can write the representation. Okay, so that's why the expression looks complicated. It does not immediately reveal anything about the behavior of the solution. I'm interested in finding that, not just about the solution. Hence, we need to do further analysis. Okay, so the one important thing is that this is what I want to do. How do I do a qualitative analysis? This is positive all the time. How do I do that? I can't do it immediately. It's just like mod y by y naught, irrespective. I don't know a minus by naught is positive or a minus by is positive. If I know that if everything is positive, modulus I can remove, then I can write the solution here. Once I can write the solution, I can take the limit. A is positive. You see, this is still to be cleared whether this factor is solved, which I am going to do, which you can do it with certain assumptions on the equation. For this equation, that's why I said you can do some analysis on this differential equation. The existence and uniqueness comes into picture. So I will tell that one. Before that, let me see if I can remove the modulus, I can write my solution in this form. In that case, this factor e power minus a into t minus t naught goes to 0. So this factor will go to 0. So yt will go to a by b. So you see, as t tends to infinity, yt is no longer going to infinity. There is a limiting population. And you can also see that this function is increasing, sometimes decreasing, depends on where your y naught is. That also I will show you that one. So here is an important thing. This is actually true. This factor a minus by naught by a minus by is positive. What I'm trying to say is that a minus by naught and a minus by naught is a given thing. A is given, B is given, y naught is given. What I'm trying to say is that if a minus by naught, so can immediately calculate immediately because that's a data. If this given data is positive, this data is also positive. That's what I'm trying to say. If this data is negative, A minus by naught is negative, then A minus by naught is also negative. A minus by is negative. That means the structure is remained all the time. So this fraction will be positive all the time. And this is you can actually prove what is called using uniqueness of the solution. Where the equation which we have considered has a unique solution. It cannot have two solutions. Okay, this is a factor to be proved. That's where you study existence and uniqueness result. This problem is a nice problem. You can prove unique local existence, not global existence. There is a local existence means it will exist only in a neighborhood of T naught. It may not exist for all T. Okay, but certain cases you will get global existence. All that can be proved without basically solving this equation. I don't need this expression to do all this analysis. I can analyze my ODE and derive that this is a positive quantity all the time. And once that is a positive quantity, this will be positive, and you can take your e power that one, and I can take y together, and I can take. So how do I prove it? Let me give you one quick proof. After that, I'm not going to give you the quick proof. How do I prove using the uniqueness? And there are other things to study in ODE, the kind of equilibrium point, shape of the curve, stability of a equilibrium point, accelerated and decelerated curve. So okay, this I don't want to tell. The estimation of A and B are also important, that depending on the populations, pollution, sociological spends. There are so many other things in it. In a more realistic model, the model I considered is just to interaction between the same species. There are other things one needs to consider, more than one species, their interactions, unforeseen issues like epidemic, natural disasters, which may lead to more complicated equations. So let me tell you one interesting thing about this equation. That graph I will tell you. Let me go back to this equation. So look at this equation. So if it is a one-to-one in a personal talk, I will be able to ask you how you understand. Look at there. Why identically zero is, so forget about this initial condition. Don't take this initial condition. Forget about this initial condition. Take only the differential equation dy by dt equal to this one. If I take dy by dt equal to this equation, you can see that yt identically zero is a solution. So if your initial solution is zero, your solution will be zero permanently. You are using the uniqueness. What I'm saying is that from the same initial data, you cannot have two different solutions. This important assumption of uniqueness, that it cannot have more than one solution, is a thing to be proved. That's where you need to have existence. There are various methods to solve that one without solving that equation. Very general equation dy by dt equal to f of ty. You can talk about the existence uniqueness using the continuity of the function f. Here the function f is ay minus by square, and the Lipschitz continuity, all that is required, which let me not do that one. One solution you can immediately think is that y identically zero is a solution. So that's a constant solution. So if yt not equal to zero, yt will be zero by uniqueness. Similarly, look at once more. Yt identically equal to a by b is a solution. You can see that. So whenever the right hand side is zero, dy by dt equal to zero, and yt will be that constant. You see? So you will get, this is called equilibrium point. So your analysis of equilibrium point. So your yt is equal to, so yt not equal to zero, yt will be identically zero. Similarly, yt not equal to a by b, then yt identically equal to a by b will be a solution. So I have two solutions now for the differential equation. So this line, this black line, the t-axis, this t-axis is a solution. So if I have an initial data here, it will be solution. Similarly, if yt naught or y0 you can take. If my y0 or yt naught equal to a by b, my yt will be a solution. So you have a trajectory here. This dotted line is a trajectory. This t-axis is a line. Now you use your uniqueness. So you can't have that. So any solution starting here. Suppose your yt not equal to anything between 0 and a by b, then that solution has to remain here. It cannot cross this line because it's a solution. It cannot cross this line, it's a solution. So you see, you have a two important qualitative reduction. So if your yt naught equal to y naught is between 0 and a by b, then your yt will become between 0 and a by b. This is exactly this condition. So if this condition is between that one, it will. Similarly, if yt naught is greater than a by b, then your whole trajectory will remain in this way. Similarly, your yt naught is less than 0, it will be below here. So between these two, so these two constant solutions divide your axis, y-axis, into three parts, and anything starting here, it will remain here, and anything starting above a by b will remain there. For this, I don't need the concept of solution. That's what I'm trying to convey to you. And then you can study its dy by dt, d square y by dt square. You can see that if I have my yt naught is between 0 and a by b, then I can show that my dy by dt is positive. That means my solution will be increasing. So whenever I have a initial population between 0 and the limiting population a by b, then yt will remain between, all my solutions will be between. Not only that, my yt will increase. It will be an increasing function. Then you can analyze your d square y by dt square. Then you can see that d square y by d, that's acceleration. Then you can see that your d square y by dt square is positive till the population is a by 2b. And that's a half of the limiting population. So if you have a half of your limiting population, your dy by dt will be positive, d square y by dt is positive. That means not only you have growth, you have an accelerated growth. The growth will be faster. And then the population reaches the half of the population, you can see that interactions are taking place more and more. Slowly the things are coming into picture. Till the population, half of the population, you have everything enough in your city. But then the population reaches half of it, they start fighting between the thing. There will be interactions between the people, between the bacteria, and still the population will grow, but in a decelerated way. And that's why the solution graph will be a S-shaped curve. And I'm deriving all this without solving the equation. That's what you have to understand, because most of the time you will not be able to solve the equation. So of course, if you know the equation and if you know the solution, you will be able to do this one. The above curve is called a logistic or a shaped curve. Note, a by b is the limiting population. Okay, so as I said, there are various other populations, there are various population models. You can incorporate other species. So you can have a system of equation. There will be two species, X and Y. X will be one species, there will be another species, and then these two species will interact. Among the single species, they will start interacting. According to that, various terms will come into the picture. So you will get a system of equations in that. And there are people studied such population model. You probably heard about prey-predator model, rabbit and so you will have the kind of the fox rabbit. If the population of the rabbit increases, enough population, and then when you have enough rabbits, you have enough food for the fox. When they start eating the rabbits more and more, the population of the rabbit will reduce, and then the foxes will increase because they got enough food. The number of foxes will increase, and then they will not have enough food. That's why it's called a prey-predator theory. One will go up, other one will go down like that. When this goes up, other will go up. and then you will not have enough food, then this will die. So you have this balancing act. Is called prey-predator theory in ODE. So now let's go to a second equation. This is an atomic waste disposal problem. Okay, this is an atomic. My time is up to 5:10 or something.
You can take up from 75 to 80 minutes.
Okay, fine. So I will do a quick, because I will leave something. There are a lot to tell. I will. So let me tell you another atomic waste disposal problem. And this is a problem actually given by the US government to the scientists to do it. That. So let me just explain to you. I will not return everything. It's a typically the atomic waste sealed it in a drum. And then the atomic waste is a very, it can do things, harm to the people, right? And so the atomic waste are sealed it in a drum and then used to dump it in a sea. And when you may dump it in a sea with zero velocity, but then the velocity due to gravity will and buoyancy force will, and by the time it reached the bottom of the sea, it can get the velocity. The velocity will keep on increasing, and by the time it may reach the bottom, it will have certain velocity, and it's possible that the drums will break. That will be hazardous. So the problem given to that, all the parameters, everything given, where they were dumping where the sea height is around 300 feet. And that parameters are all there. So they want scientists whether this problem, whether the drums will break or not by the time it reaches the bottom of the sea. That's what they want to do things. And they given the problem. So what do you do? Naturally, how the drums will move under this one? You have a Newton's law of motion. So you have your mass into acceleration. That's m into. So yt is the length distance from the surface to the is the position of the drums at time t. So the particle from the surface velocity is 0. So at time t equal to 0, y0 is 0, and then yt will acquire the velocity, and then you will have the modeling mass into acceleration is equal to alpha. So you understand all the forces. There are 3 forces acting on this one. This is the force due to gravity, buoyancy force. Then there is what is called a drag force. Drag force is generally proportional to velocity. Okay, so there are other models. So we are replacing this all these parameters. There will be some taking. So you have a linear equation again, simple linear equation. So this linear W equal to mg, all that you can do it. Maybe if you want, you can look into my book, which I referred here, or any other book where for this. So typically you have a problem. WB, everything is known. The velocity at the time t equal to 0 is 0. Here I am going to show 2 model. I'm going to show you again a linear model. The same problem, but the linear model you can completely solve it, but it doesn't give you the answer. So you have to readjust that. So the modeling is also important. That's what I want to show this one. Why it will not solve the problem which the government gave it to the scientist. So this is a linear model, which a linear model with right hand side, constant right hand side. This is given to you, and this linear model you can solve immediately using integrating factor. So you get this solution. So you have an immediate solution. This is known to you, and CG everything is positive. You see, so as t tends to infinity, you know, Vt tends to W by C and WB by C. So the Vt, the velocity tends to WB by C as t tends to infinity. And this thing is approximately 700. So the value, so the question is that it is what actually the government wants, whether the velocity will reach certain velocity. And they knew the velocity to be reached is 40. If the permitted critical velocity is 40, there is a possibility that the drum will break. Okay, if the W minus B by C is suppose less than 40, it will never reach the velocity 40. In that case, the problem is solved. But the crucial thing here is that we do not know this Vt goes to W minus B by C only when t tends to infinity. But what we want is that what would be the limit of Vt when t tends to t equal to some t bar. And we do not know what that t bar is. That's where the problem. That's a part of the solution. At this stage, you do not know the what Vt bar we want to find. The reason is that we want to find Vt. Once you have a Vt, we do not know what time it will reach. So this immediately won't answer. If this number happen to be less than 40, because the permitted velocity is 40, then it is immediately thing. So what we remains to show that Vt does not reach 40 by the time it reaches the floor. Naturally, Vt can up to 3, depending on the length of the thing, it can reach 40. But what the problem, the practical problem is that Vt does not reach 40 by the time it reaches the floor. Okay, so that's what we want to. So you want to know the velocity, not with respect to the time, you want to know the velocity with respect to the distance from the surface of the sea. Okay, so the distance at the bottom, the total distance of the bottom where these were dumping were some 300, doesn't matter which is. So the issue is that you want to find the velocity not with respect to time, you want to find the velocity with respect to distance. So you want to remodel this equation. You see, so that's what we are thinking. Now, so y is the position. So we let Vy be the velocity at the height y measured from that. Of course, if Yt is the position, your Vt is equal to V of Yt. So the small v is the velocity with respect to distance, capital V is the velocity. Of course, this is connected. So you have to rewrite the differential equation. Once you rewrite the equation in terms of V, you have a nonlinear equation. You see, the same linear model gave you the complete solution, but it didn't give the final answer. So we remodel it, you got a linear model and non-linear model. As I said, non-linear models are difficult to solve. But again, as I said, I'm showing you the simplest equation, not that these things will work all the time. Fortunately, this equation, again, you can solve easily by doing this. You can integrate with some trick. Okay, it's not very difficult. You would have seen such equation. And you get this equation in an implicit form. You have an explicit equation. You don't have an explicit equation. So you have your V in terms of Y in the implicit form. So we would like to, but then this is a very complicated algebraic equation. It's not a differential equation, but it's an algebraic equation. And it's not easy on, probably it's not possible to solve explicitly for V in terms of Y. That's the problem. So you see, in a linear model, you have a complete answer, complete solution. It doesn't give you the answer you want, but then you convert it into a non-linear model. It gives you the solution, but unfortunately, that solution is in the non-linear model, in the implicit algebraic equation. And that's what you do with that one. You can't do much, but then you do a numerical computation. You can do, that's where your scientific computation and numerical computation is. So you want to compute the V of whatever distance of the surface to that bottom, and it is computed, and we have seen that V of 300 is approximately 45, which is above the permissible limit of 40. Okay, so you got an answer, end of its solution, not exactly, but approximately after from that solution. So what happens? Tail to the tail, this problem was initiated when the environmentalists and scientists questioned the practice of dumping waste material by the Atomic Energy Commission. After the study, the dumping of this low-level atomic waste at sea was forbidden. That's another issue. So you see how a certain analysis, certain way of remodeling this equation is not about just solving equation and getting solution. You have to give answers. Now let's go to a third thing, that's a little more detailed analysis is required. So let's try to do that as much as possible. Yes, Kanbar. Somebody has any?
Hello, good evening, sir.
Yeah,
Sir, I would like to say something just like the methods of analysis.
yeah.
Sir, we have a famous partial differential equation
Oh,
named the
so let's
Schrodinger
not get
equation.
into other things now, that we can come at the end or discuss later. If it's not immediately connected to this, we will ask that question end of it.
Okay, thank you, sir.
Yeah. Because we don't have that much time to interact or discuss that. Okay. Yeah, you can ask at the end
Yes,
of the
sir.
class.
Yes, sir.
Okay. So let's now go to a mechanical vibration system. This is a very, very important system. Okay. This is what the fundamental of any mechanical vibrations, sir. Okay. Because whenever you have a vibrations, the vibrations can harm. For example, when you are riding a bike, it can. When you are shooting a gun, it can create vibrations. So you have to control the vibrations, sir. So how do you do? So it's a vibrations with respect to a spring. I don't have a thing. Suppose you have a spring. When you pull it here, when you pull the spring, it will start vibrating. And what do you know about it? These vibrations in principle will not stop using because of the Newton's first law of motion. When the vibration sets in, it continues to vibrate when you pull it. Unless there is an external registration, unless some external disturbances coming into it. That's what will happen. If you have a vibration, if you go and hit a hump, it can create vibration. The vibrations can remain, or the vibrations can increase, or the vibrations can reduce. In a normal thing, in a mechanical thing, you want to remove the vibrations. So how do you model? You have to model it by understanding all that one. So there are quite a few things which the details of the modeling, I don't want to explain it to you, but I want to apply Newton's law of motion, and then you get some equation of this form. So you are basically, suppose you have a spring, you put it in a liquid, it will create a damping. So it will reduce. One way of reduce external disturbance will be there. Other things will be there, but one way of reducing the vibrations, that's why you get the shock absorbers in bikes will do exactly that principle. You want to reduce the vibrations and without anything. So there's a modeling way of doing it. You understand that one. So when you have a spring vibrate, if you put it in a liquid or something, it can damp it. It's called a damping. So giving a damping to your mechanical thing, that's what when you construct a building or construct a bridge or construct anything, you have to provide enough damping. If you don't provide enough damping, that building will collapse. That bridge will collapse. That's why many times, because they don't give proper damping. How do you give the proper damping? Through your material, how they construct the thing. So everything will have thing. So in a spring, this is the mass of that. You have a mass hanging along a spring. That's a M is the mass. And then for a spring, according to the strength of the spring, what we call it a spring constant. And this is the damping parameter. And then this may be the external force. So F is your external force. Damping, C is the damping. And that will be proportional to all that is mentioned, damping or drag force, it is called. And then your mass. So this is your very familiar equation, you see. This is the one equation you study in your thing. What do you do when you study a second order equation? You just write your complementary function as a particular integral and you write your solution. You most of the time don't understand why we are doing, why a complementary function, why a particular integral, all that. To understand all that, you may require good concepts from linear algebra. As I said, I will not do that way. But you have a familiar equation. This is the second order linear equation. So I'm going to do some analysis based on if there is no damping, if there is an over damping, and there is an under damping. Okay, I'm going to, there is an external disturbances. That's what the rest of the talk I'm going to tell you this one. So second order linear equation with constant coefficient. And you know that how to solve it, at least when f equal to 0. There is no external disturbances. This is a homogeneous equation. And homogeneous equation, you call it a complementary function solutions. Okay, and then you know two independent solutions. You have plenty of questions to ask for a second order equation. Most of the time teachers tell you that there are two independent. What do you mean by two independent solutions? Why only two independent solutions? They may give a reason it's a second order, but you have to have a kind of an argument why second order equations have two independent solutions. That's where you are a bit of a linear algebra. It's a very surprising. You have a linear equation which is working on a function space. Function spaces are not finite dimensional. So to understand that, but then what you are telling is that two independent solutions form a two-dimensional subspace. That's a very, very interesting and result that homogeneous equation has two independent solutions. It is a result which is a non-trivial result to be proved, even though it can have many solutions, infinitely many solutions. What it says that it can have only two independent solutions. That requires a proof. That requires not just from one equation. You want to derive for general linear equation with constant coefficient, or just linear equation, nth order linear equations. So that's where stronger things which we are not going to do it here. So the interesting thing is that this is about the mechanical vibrations, but then this is where the abstraction of these things comes. Once you have these second order equations, it doesn't matter it's coming from mechanical engineering. So as a mathematicians, we quite often don't even look at it. When you do only analysis, you do it. That's what you do it in your BSc and MSc. You have a linear equation, second order equation, complementary function, write down your solution. And if you have an F, you write down your particular integral, you have stopped it. But then the engineers want solutions. An interesting fact is that completely a different subject and electrical circuit. These are the fundamental two distinct areas, right? One is the mechanical engineering, other one is the electrical engineering. In an electrical circuit, this is an RLC circuit, resistance, capacitance, and inductance. If you model this equation, you can get the same. This is a basic LCR circuit, and this is the fundamental circuit in any circuit to begin with. And this is what you have to understand. And this is the voltage drop. Okay. And the voltage drop or the current charge Q, you can write the equations in terms of Q as a charge, or you can also write the equation in terms of the current, because there are relations. So you see, I'm not going to give the modeling here. You can do the modeling and you get the same equation. You see? So here is the inductance and here is the resistance. You see the resistance working like a damping. As I said, if there is no damping in the building, you will have problem. But so that's why the resistance, correct amount of putting resistance is important in any circuit. And this works like a thing. And here is an L. It's like a mass. And then Q by C. This is the cup. And this is the applied force. Okay, some electromotive force. So the interesting thing is that for mathematicians, equations are coming from different areas. But mathematicians don't want to work for separately for them, right? We want to give a common general solution. So we want to treat equations coming from completely different areas as a single equation, and we want to write the solutions theory to be developed for a general equation, and whoever wants can use according to their preference. This leads to abstraction in mathematics. That's what you see in abstraction. So the abstraction is not just some kind of generalization. Abstraction, just putting it in the abstract form. Abstraction gives you very, very general thing, and you are actually trying to solve many problems from different areas. That's what you are doing. Okay, both are second order linear equations with constant coefficients. So I want to discuss little bit about these equations, how the damping changes to you. So I want to, you know this complementary function and all that, and you know how to solve it. And you also know how to solve it for FT. But I want to know the difference between C and there is no damping and there is no F. So we want to see that solution. So this is called free undamped vibrations. That means there is no external force F equal to 0, and then there is no damping. In this case, it's a simple harmonic motion, right? You know that simple harmonic motion. If this is 0, this term is there. This is m into d square y by k y equal to 0. Your complementary function will be comes from the complex analysis, right? The roots are not real. So you see, and you can write your solution here. And this omega naught is k by m. K is the given quantity. This is the given quantity. So for every system, every mechanical system, you have an omega naught. Omega naught is this one in this particular case. And this is called the natural frequency of the system. Look at this. This is the mass and this is the spring constant. That's a given. So it depends on the spring constant. So it gives you a produces a natural frequency. So any mechanical system you create, there will be a natural frequency. And omega naught is given by the natural frequency. And this is the solution. And this you can write it in this one. And physicists like to write this way because for them this is the amplitude and this is the frequency. If omega naught, how big is, how small it is, right? See, you see omega naught here. And this is the period of that one. So omega naught is small. You have your T naught becomes bigger and bigger. Okay. And omega naught is large. Your T naught becomes big. And this is the phase. When it will start, phase difference. And you will get a periodic because cos is between -1 and 1. And this is periodic. It period changes and it changes with the period minus r and r. You see. So and this is the typically the Newton's first law of motion because there is no damping and there is no external force and it works because of the just natural frequency. So you pull it, it keeps on oscillating with the same frequency. You see. The frequency is the same and between these two, this is the time period and this time period is 2 pi by omega. You see, omega naught in this case, not omega. So you see, your T naught is between, and you have a very nice oscillatory behavior, and the vibrations will never stop. This is what, if there's no damping, no external force, no vibration. The vibrations will remain as it is. It's not going to die down because to die down, it has to violate your Newton's first law of motion, right? You need external force or you need something else. You have to put it in a liquid or something like that. So this is the case one. So let's going to understand the case. Another case. This is the damped free motion. So there is no external force and C not equal to 0. When C not equal to 0, you get two roots. Okay, R1 and R2 are the roots of the characteristic equation. You know that complementary function and you can write down your solution. You see, if you see, look at this first case. C square minus 4nk is positive. What does that mean? Your C is sufficiently large, bigger than this one. And these two are given, M and K are given. So if you put the C positive, not only positive, C square is positive always. C square is sufficiently large so that this is positive. In that case, of course, R1 and R2 are negative. And you get this solution. So the roots are positive, real in that case. You get the roots real, R1 and R2 are real, and you get this root. And on the other hand, it's a just sufficient damping. C square equal to 4nk is 0. You get this solution. Of course, there is an T going to infinity, but then you have a... So you look at these things. The first case. First case, R1 and R2 are negative, which you can show it. When you have the roots are negative, this goes to 0, this goes to 0. There's no vibration. There are no oscillation. So you have enough enough damping given to your mechanical construction, like a building or a thing. You have your no oscillations will happen and it will go to 0. Your YT will go to 0 as T tends to infinity very rapidly because it's an exponential decay. When your damping is just sufficient, you have, there are two terms here. First term, this goes to 0, but T tends to infinity. So there is a infinity into 0, indeterminate form. But you know that exponential goes to 0 faster. So even though T tends to infinity, still there are no oscillations. And e power minus et goes to 0. Not only that, this product, any polynomial into exponential will go to 0 if the exponential goes to 0. Now look at here. You have some damping, But the damping is so, this is what, if you don't do proper constructions, the building will collapse. If your damping is that good construction, good thing, you provide sufficient material. If this is negative, when your damping C-square is less than 4K, in that case, the roots will be negative, roots will be complex. This is the single root solution. These roots will be negative and your solution will be this one. So you see this second term, A cos mu t plus B sin mu t oscillates, but sin and cos are bounded. So even though this is oscillating, this is bounded quantity. Once this is analysis, small analysis, you should do it. Even though this is oscillating and but bounded, but this goes to zero. A bounded quantity into goes to zero. So this goes to zero in an oscillatory fashion. You see, if these two goes to zero without oscillation, the second term goes to zero slightly slowly, but exponential will take over as t tends to infinity. And this goes to zero very rapidly. This also goes to zero very rapidly, but in an oscillatory fashion. So this is what is called, the first two cases goes to zero, yt creeps back to the equilibrium point, because y equal to zero is a solution, because f equal to zero. So y identically equal to zero is an equilibrium solution. That means your initial data is zero, your solution will remain there. But there is a perturbation, it will go back to error. This is what called a stability analysis, which I don't want to discuss too much here. So y identically zero when f equal to zero is a solution. So your solution initial point is zero, your solution will remain there, it will not move. The question is that if I change a little bit, will the solution will come back to my original solution, zero solution. And that's what in this case. Third case also is that the moment there is a damping, the solution will always goes back to the original zero solution. The only thing is that if the going back will be under damping system, it will go to zero. So there is no danger in any of these things. So the moment there is a damping, there's no problem. Every solution good thing, your mechanical structure will be safe. But the issue comes when f not equal to zero, because there will be an external force, external collapse, there will be a heavy wind, there will be a heavy rains and other things. When your mechanical vibration, your buildings, your structure can sustain that external force. And that is what we want to say. Then that's where you need more damping, even to take care of your external disturbance. Okay, right now it doesn't matter because there is no external thing. That means if you make a building, if everything is fine, no external force, that building and bridge will remain as it is. As long as there is a bridge and there is no wind, there is no external things, there is no vehicles moving along the bridge will remain like that. Okay, it may decay, but it will remain. It won't collapse. Okay, and then in the third case, it will do this one. This will be the solution, and it will. This is the phase difference you will see. This is the free undamped thing in the third situation. Okay, this third situation. Other one is faster decay, not oscillation. Only in the third case. So you have a starting. Initially, you may have something, but eventually it will decay with this. Oh, now, as remarked, the motion dies out if there is damping in the system. In other words, the initial disturbance is dissipated by damping. This is why it's very useful in mechanical systems. It can kill undesired vibrations like shocks transmitted in an automobile. That's what you do with your shock absorbers. Shock absorbers are precisely giving damping. Principle behind shock absorbers, momentum from gun, etc. Otherwise, if you shoot, the gun will go, the bullets will go with the same force, the barrel will come and hit you. It shouldn't happen, right? Okay. Now let's go to a situation where the more dangerous thing is that f not equal to zero and there is no damping at. Okay, that will come to the last stage of the talk. Quickly, another 5 minutes I will do quickly. So we'll go. So suppose you take a particular thing, then only you can solve it. So you are taking f not equal to zero, c not equal to zero, and you can find one of the particular solution here. For how do you find a solution? You want a solution of the homogeneous equation with f equal to 0. Then you find a particular solution. And then this is your complementary function phi. This is a solution obtained earlier. Okay, this solution I written as y. So you have your phi and then you have your yt. And you can show that phi goes to 0, you already proved as t tends to infinity. So you see, phi is a solution of the homogeneous equation and go to 0 as explained. And then for large time, yt behaves like your ypt. It's very important, you see. And this yp is called the steady state. So eventually your steady state of the solution as t goes to 0 will be yt, and phi t is only the transient state. These are terminologies coming from physics, okay? So there is a changeover taking place. Okay, and now let's come to the most dangerous thing where you have no damping, but you have an F. Yeah, and this is your F naught again, and you have your natural frequency. Now there are two situations. You have this is the frequency of the external force. Suppose a wind is coming or something coming to that, or the vehicles are moving along the bridge. It will give you some frequency to the bridge. Okay, because it will start vibrating due to the vehicle movement and other things, right? And the wind movement, if there is a hurricane or something, there will be a wind movement, that one. That will have its own frequency. Let's assume this frequency. This is your natural frequency. Now, there are two situations. One is called the natural frequency is different from the external frequency. This is what is called without resonance. There are more things to tell about resonance. So let me not do it. When omega not equal to omega naught, because omega, it will be the root of the thing. So if your frequency has the same root as your complementary function root, then it will be a problem. You can't solve it easily, but you can still solve it in this case when omega not equal to omega naught. Then you have your solution, and this is different. If this is equal, this is not your particular integral. And then again, you know that this is oscillatory, and this one will go to the thing. So you have no issue. Its analysis is similar. So if you have a case, your external frequency is different from your natural frequency, that's no issue. It will think. The problem is the more serious case in the mechanical vibrations with resonance, with C equal to 0, F not equal to 0, and omega equal to omega naught. In this case, this will be your equation, you see, C equal to 0. And this omega naught and this omega naught is the same. So instead of omega, you can write more general thing here, and then you can write your solution in this form. Now look at here. This is the complementary function. Look at the last part. In the last part, there is t sine omega naught t. In earlier situation, you got exponential. Now this is a bounded quantity. Once there is a bounded quantity, this term will take over. So as t tends to infinity, this may go to oscillatory part. Because of this first part, homogeneous part, it will be oscillatory. Same without reduction, because it's a C equal to 0. You need C not equal to 0 to reduce that. So this will not reduce, but it will not go. But this will go to infinity. You see, according to infinity or minus infinity. So your solution is blowing up now. So in a resonance case, your solution is blowing up. So force, this is called your forcing term is in resonance with the natural frequency. It will cause unbounded oscillations leading to mechanical catastrophes. So you see, your solution will, vibration will shoot up now. So that's why, so if you construct a bridge and the vehicles are moving with the speed and it will create a frequency, if that frequency matches with your natural frequency, the vibrations can, and this is actually happen in, so you have to be careful. So you have to create a bridge or a building in which your damping should be in such a way that, or its frequency in such a way that it will never match with the other one. So no resonance will take place. Okay. So this is what happened is a thing It's probably you can see in online or something, and you can see what happened in a Tacoma bridge collapse on November 7, some 60 years back. The system needs to have sufficient damping. Okay. And so this happens. So you can Google it for Tacoma. It's happened. The bridges start vibrating in the early morning, and the vibration becoming larger and larger. Of course, people noticed, and unfortunately, people stopped moving along the bridge. And by 11 o'clock, bridge collapsed. This is also responsible for the collapse of Broughton Suspension Bridge near Manchester. Okay. This you probably know. When the soldiers are marching along a cadence, the soldiers will march not like we walk, right? The crowd walks. The soldiers will walk in a very systematic way, creating a big damp in this thing, frequency. The frequency will add up. So there will be a very high frequency developing. And then if that matches with your bridge, even if it is high, and it can collapse. That's why soldiers marched in cadence over the bridge. They will unload. If there is a very long cadence of marching of the soldier, they will never allow the soldiers continuously cross. They will break it. A set of soldiers will cross to the other side, and then another set of soldiers will cross. So the batch by batch it will go to avoid the large amplitude for setting up. This frequency was equal to. Thus, large oscillations were induced and the bridge collapsed. This is the thing. So you have to be careful. So you may think that creating a resonance is bad. Yes, in mechanical vibrations, having such a thing. But as I said, for mathematicians, it's the same problem solving. But when you do this one, this is exactly used to their advantage by the electrical and electronics engineers. That's why it's a reason soldiers are ordered to break cadence while crossing a bridge. Among many similarities with the mechanical vibrations, electrical circuits have property of resonance. So you are able to see your TV, radio, mobile, everything, because they everything make in resonance. When you have a phone number, somebody is ringing you, basically what they're getting, the external frequency coming from outside, putting into resonance with your natural frequency of that one. You see, so in the electrical or electronic system, they adjust. When you are tuning a camera, they adjust their capacitance in such a way the resonance external frequency. That's why you are able to tune a particular radio station, because the resonance is coming, frequency is coming from that particular frequency. So you adjust your capacitance in such a way that it is in resonance with. That's why you say, oh, we need the same frequency, because you are creating an resonance, and then it's changed until it agrees with the frequency of the external. The amplitude of the current produced by this signal will be much, because it's increasing much greater than that of other signal. Other signals are also there, so that we get the desired signal. You see, desired, not signal, you get the desired TV station or whatever it is. So I will more or less stop here, and then there are other equations. These are the non-linear models. These are all models. Some of them create a Duffing equation, and there are kind of a what do you say, Rayleigh, other type of van der Pol equation. Actually, this is post when the van der Pol was working for the Philips company in 1927. So then this is the coming from the weather prediction. So this looks like a very little nonlinear equation. It leads to chaotic behavior. For a proper choice of R, sigma, etc., they observe chaotic behavior. Okay, so there are many other equations. This is what I told in the beginning. There are two species, and there is an interaction between a species X with a species Y. And you see the species that are rabbit and foxes, population, prey predator things. Okay, so you see if this is bigger, if B is bigger, that means the foxes are eating rabbits, and like that. This is less you have to choose your signs exactly where you put the signs, and you want to study such equation. This is called Lotka-Volterra pre-predator equations. So there are many such equations, hundreds and hundreds of examples you can give. But mathematicians want to give a very general theory, not deal with every one equation. You want to have a set of equations, x1, x2, xn. So you want to have x1 dot equal to f of x1, etc., x2, x2. So you will have a system of equations. So you want to study, give as much theory as possible for a system of equations. And study, and you may not be able to do it explicitly. Naturally, non-linear equation, you can't write down the expressions. Yeah. So thank you very much. Yeah, these are the two books if you want to have. So what I have presented here is first chapter of my ODE book. If you want to learn more ODE, you can look into this. There are 40 lectures in this one. And these are the PDE lectures, and these are some advanced PDE lectures. These are all available freely, all these NPTEL video courses. If you want to learn any of these things, you can do that. Thank you. Thank you very much.
Thank you, sir.
Yeah.
If anyone has any questions, then you can raise your hand. Yes, proceed.
Yeah.
Jai, Kanabar Jai.
So maybe I'll stop sharing.
Yeah.
Yes, sir.
Okay, this meeting is recorded, is not stop sharing, is not working.
Okay, I'll stop it from here.
Yeah, I can stop it for me.
Yeah.
Yes.
Okay. Kanabar Jai.
Yeah.
Good evening, sir, and all people.
Yeah.
Sir, I am talking about a beautiful and the most famous partial differential equation named Schrodinger wave equation.
Mm-hmm.
And we have some also set of connected equations like Dirac's equation,
Mm.
which contains a beautiful number named iota, imaginary number.
Mm.
So while I was analyzing these equations derivations, there was a step from which iota came into the picture,
Mm.
and it make the entire equation complex.
Mm.
So what physicists do that they can't measure that complex thing, so they squared the modulus term
Mm.
and assigned it a probability function. That was done by Max Born in 1926. So now the famous mathematicians like Roger Penrose and everyone claims that quantum mechanics is incomplete and undeterministic in its nature by iota.
Mm.
But I have some proofs that it is not the incomplete nature of quantum mechanics.
Mm.
This is how the picture of iota comes in, and iota brings the information collapse in the wave equation by the Schrodinger.
Mm.
So that was just like the part of qualitative analysis, and that is also a beautiful property which
Mm.
we have not yet discovered. But iota is a number
Mm.
used by universe to describe the time dependent properties,
Mm.
and that was the only reason that information does collapses in the singularities
Mm.
which are not yet satisfied by the quantum mechanics.
Mm.
So I would like to review your. I would like to seek your guidance on the method of separation of variables which we use to solve Schrodinger equation,
Mm.
which eventually leads a time-independent equation and then generates the entire problematic view.
Yeah, sure. We can have sometimes we can come more whenever we get an opportunity, we can do that one. I agree with you. Probably quantum mechanics is not complete. That's what I always take it, right? You started with a not a Newtonian mechanics for the natural thing. Then the velocity is high. You got to the relativity. Then later came this quantum mechanics where the Newtonian principle is not valid when the particles are very small. For example, you cannot exactly say where the electron is at time t. So you can only say with probability. That's why this your modulus mod psi t square coming. So that interpretation comes through your function, wave function and probability. So it's replaced by the position and velocity by the operator and the wave function. So I agree, even that may not be complete. Because iota, etc., I do not know much, but yeah, we can have discussion when
One thing I would like to add on, sir,
yeah,
that
sure.
if we look the paper published by the Schrodinger in 1926, the first thing we will look upon are the assumptions that Schrodinger used to derive the equation and the psi function that were itself complete in nature, because he also considered the variables force and momentum.
Yeah.
And then the iota came in the picture. So I am telling that quantum mechanics is complete, but it is the nature of iota that hides the time dependent properties of quantum states, which eventually leads up to singularities in the general relativity, as the gr and the Minkowski space coordinates are also found with iota. So when the iota gets vanished in both the theory, it also takes up the information of the time dependent properties of particle, and there comes the picture that we don't need a theory to contribute in qm and gr. That is the nature of iota.
Of course, I am not familiar much with it, so it's probably it may not be right on my part to comment too much on that, because my knowledge in quantum mechanics is very limited. Yeah, but we can have a chat or a discussion at some point.
Yeah, so can I have some of your contact details so I can contact you about this topic, please?
Yeah, you can see, you can come to IISC. Anyone, somebody else also asked. So you can look into my homepage in IISC Maths department. You will have the details. You can send mail. That's not an issue.
Okay,
So
thank
someone
you,
else
sir.
asked. So you can, it's the best way to contact me through email.
Yes, sir.
Okay, and then always write that you attended that. Otherwise, we'll have too many mails, so that you can
Yes, sir.
mention. Okay.
Yes, sir.
Yes, any other?
Next is Sujit Bhattacharya.
Hello, sir.
Yeah, good evening.
Good evening, sir. Good evening. And also happy Diwali, sir. I'm Sujit Bhattacharya from the University of Bardwan, West Bengal. So, sir, I was doing my research work on Riemannian geometry. And thank you for such a wonderful lecture. And, sir, I have a question. Sir, can you please tell something about modifiers on differential equations?
Of course, I know I can tell a lot of things, but probably it is very, you need much more time. You can also have a look at my PDE book. It's very well mentioned there.
Okay, sir. I'll definitely.
So
I seen the
modifiers
book
are in
in
connected
our.
with a previous person's thing. Dirac basically understood Dirac delta via modifiers. Because Dirac delta, to understand Dirac delta properly, the mathematics was not sufficient at that time. Because he was looking for a function which is 0 except at x equal to 0. At the same time, integral of delta x dx equal to 1, right?
Right.
Mathematically, it is absurd because a function which is 0 except at one point, the integral value is also 0. It cannot be 1.
Right, sir.
But Dirac had a physical interpretation. He is trying to understand probably how do you act on a unit force at a point. But a point is a mathematical concept. It's not a physical thing, right? Nobody can draw a point. So practically, see the physics, there will be always experimental error. So when you say that point force is acting at a point, you can't do it. But so what you can, the best you can, so for example, when you want to understand the temperature at a particular point of the body, how do you measure? You put a whatever it is measuring thing on that point, but a point is a concept, you can't put it. So what you basically get is the temperature not at a point, average temperature in a small neighborhood of that point. Okay, so basically your modifiers are that. Your point is so your unit force is not in at a point, but a force is acting in a epsilon neighborhood of the point. So it's a rho epsilons or something. Rho epsilon of integral of rho epsilon equal to 1. But rho epsilon, you are relaxing instead of Dirac delta x equal to 0, except at x equal to 0. You are demanding rho epsilon of x equal to 0 for all x, mod x like greater than epsilon. So outside minus epsilon to epsilon, your rho epsilon is 0. So you are allowing slitting minus epsilon to epsilon, you can have a non-trivial value. That way you can put any small epsilon and you can put 0 and shoot up something and come. So you see a relaxation of little condition in align with the practicality, you have that kind of force acting. That means if your instrument is very good, you can put your instrument exactly, you can act. That's why you are pinching more and more. If the needle is more and more sharp, you can make a, you cannot just pinch with the needle at a point, right? Depending on the tip of that, it may create a hole, not a point. And if your needle is very sharp, the only you can say that neighborhood is small. You can never say that neighborhood is 0 at a point. So that's one thing of rho epsilon which he introduced. That's how they think. But then there are PDE, there are much more use. Rho epsilons are used to smoothen thing. Just like if there is a bad person, you have to interact with a good person to make that person bad good, right? So that's what we the concept of convolution and things like that. So you use modifiers, do a convolution with a bad function, you get a good function. And you can approximate bad functions by good functions. So plenty of usefulness. So that's what I say. You can give one day lecture full if you want.
Okay, thank you very much, sir.
Yeah.
Last is Sarvana Kumar S.
Yeah.
Yeah.
Yes.
Sir.
Good evening, sir.
Yeah.
Sir, in many practical problems, we often use numerical methods to obtain solutions subject to given initial conditions. So suppose we have solutions for two different initial conditions for a specific problem. So can we identify or approximate the solution for third initial condition without directly solving the equations?
Yes, that's what I said. You need a existence uniqueness. The third part in this call is stability result. If
Okay.
x0 and y0 differ, how much your xt and yt differ?
Okay.
And for that, you need appropriate spaces. And this is called the continuity concept.
Right, sir. Okay.
And whenever you study a differential equation, together with existence uniqueness, you also need to know what is called stability, which is a continuity. Where so you need appropriate spaces where your x0 belongs to, the initial conditions belongs to, where your final solution belongs to. It will be in two different spaces. And then you have to associate a mapping from the initial space, condition space, to the solution space. And these two spaces should have appropriate topologies. Once you have appropriate topology, you can talk about the continuity of this solution operator. And that gives you, and this is important for your numerics, because numerics you can never give x0 exactly. Initial condition. And then if your x0, y0 is close to x0, your solution is xt is close to yt. The question is that where do you measure that?
Yes.
Okay, so this leads to the functional analysis, topology concepts like metric spaces, topology, and all that comes. That's what is to understand your differential equation, you have to study that topics also well, and it's very, very crucial before you apply your numerics.
Okay, sir. Okay. And for approximation techniques, is except the perturbation method, asymptotic expansion, and series expansion, is any other possibilities to? I mean, is there
No,
any
these
other
are all
methods?
some methods. You can always do an approximation the way you like it, right?
Okay, I'm actually asking about the best method or the best approach.
That you can't say. That you can't say.
I can
Depends
say.
on this equation.
Yes.
If you want to do that best method to tell, you have to say that it is better than every other method, right?
Okay.
For a particular problem, one method will work, but another problem, another method may work.
Okay,
It
sir.
depends on what your problem is.
I'm actually working on fractional differential equations with fixed point approach. So
Fixed point
instead of
approach
using
is one way of doing that. Not only fractional, many of the problems people ODE, they do approach. Even for the existence uniqueness, you apply Picard's theorem and all that.
Okay, sir. Okay.
And
Thank you so much, sir. Thank you.
So it's there more because it's an approximation. So there is a,
Yes.
for example, if you want to even solve a differential equation, you have a global method, that's a Picard's iteration.
Yeah.
And then there is a piano approximation. Piano scheme says that you know the velocity at one point, go along that velocity, adjust the velocity, and keep on doing for every step h.
Okay.
So it's a locally you go to till the end. In the Picard's iteration for the entire period, you make an approximation. So there are various, all that is described in our book.
Yes, sir.
And it's
I
also
studied it. I
explained
have
in
one.
our NPTEL lectures.
Ah, yes. Okay. Thank you, sir. Thank you so much.
Okay.
Okay. I thank everyone for being present here, and I thank Professor Nandakumaran for being with us and delivering such a wonderful talk. Now, before dispersing, I would like to request all of you, for whoever it is possible, please turn on your camera so that we can have a group photo.